So now I'd like to introduce a few properties that people use when they're describing digraphs. The first property is called the Euler characteristic. So the Euler characteristic of a directed graph is just a number, and the number is actually very simple to calculate. Notationally, this is a Greek chi. So chi of g, if g is a digraph, or the Euler characteristic, is defined as the number of nodes minus the number of arrows. So all we have to do to calculate the Euler characteristic is know the number of nodes and know the number of arrows, and we subtract those two numbers. And surprisingly, this turns out to be an interesting thing. It turns out that the Euler characteristic can, in certain situations, tell you interesting things about the directed graph. So here we have a small example. Here our directed graph has 3 nodes and 1, 2, 3, 4, 5 arrows. So to calculate the Euler characteristic, we should take 3 and subtract 5 to get -2. So the Euler characteristic of this particular directed graph is equal to -2. The next piece of vocabulary I'd like to introduce is the notion of connected components. I like to think of these as the islands in a digraph. So the islands in a digraph are called the connected components. So here we have a small example. Here we have a directed graph with, let's see, it looks like we have 5 nodes and also 5 arrows. I guess what I'm suggesting here is we are viewing this as one digraph, but if you look at the digraph, it looks like there are 2 sort of islands in this digraph, or 2 parts to it. These 2 parts are called the connected components. So what we would say here is that this is one directed graph that has 2 connected components. Now, if you could imagine maybe maybe if we change this example and maybe linked this node to this node with an arrow, then that would reduce the number of connected components to 1 because that would connect the 2 islands, so to say. What about paths? So one thing people like to do is they like to keep track of the sort of routes one might take if they were viewing arrows as avenues to maybe move from one node to another. So for us, a path will be a sequence of distinct arrows that join consecutive nodes. So let's look at an example here. Here we have a directed graph, and it looks like this has 6 nodes and 7 arrows. And I'm claiming that one path here is the list of arrows A1, A5, A7. So before we take a closer look at this, I just want to look at those arrows. A1 is this arrow, A5 is this arrow, and A7 is this arrow. So the idea is that those arrows connect consecutive nodes in the graph. So I can imagine traveling from V1 to V3 via the first arrow A1. Then I can imagine traveling from V3 to V5 via this second arrow A sub 5. Then I can imagine traveling from the node V5 to V6, going through the arrow A sub 7. So this is a valid path from our perspective. I do want everyone to notice that when we traveled from V3 to V5, we traveled against the arrow. And when we traveled from V5 to V6, we also traveled against the arrow. In our language, this is perfectly acceptable. So paths do not have to respect the orientation of the arrows in question. There is math you can do where you restrict yourself to only studying paths that follow the directions of the arrows, but the math there actually gets significantly more complicated than the kind of math that we'll be doing in this course. So the punchline here is that paths connect consecutive nodes via arrows regardless of the direction of the arrows. And here's one example of one path connecting the node V1 to the node V6. Another important piece of terminology is the notion of a cycle. A cycle is a path that starts and ends at the same node. So here we have the same example from the previous slide. The path we took before went from V1 to V3 to V5 to V6. That is not a cycle because the start node is different from the end node. Here, I'm claiming that the cycle formed by the arrows A1, A4, A3, A2 gives us a valid cycle. So let's follow that sequence of arrows. So if we followed A1, that would take us from V1 to V3. Then if we followed A4, we would go against A4, which again is perfectly acceptable. That would take us from V3 to V4. Then if we go through A3, that would take us from V4 to V2. And then finally, if we follow A2, we would go from V2 back to V1. We traveled against the arrow, but that's fine. And that completes our cycle here. We started at V1, and then we ended at V1. So this is a valid cycle. So cycles are sort of special kinds of paths, namely the paths that have the same start and end node. One interesting number that we can associate to a graph is called the circuit rank. This is probably the most sophisticated piece of terminology we'll introduce. So the circuit rank refers to the minimum number of arrows that we would need to remove if we wanted to get rid of all of the cycles. So let's go back to an example here. So what I want to point out is that in this example, there are cycles. We just saw one cycle that took us from V1 to V3 to V4 to V2 back to V1. I can see another cycle in this graph. I could start at V5, travel through A6 to get to V6, and then travel back to V5 through A7. So that's another cycle. So the idea here is that, well, it's actually possible to break all of the cycles here by removing two arrows. If I remove this arrow A1, I can't take a path of unique arrows to get from A1 back to itself. And if I got rid of A6, I also break the cycle that we noticed over here. I couldn't go from V5 to V6 and then back to V5 with unique arrows. So if I get rid of those two arrows, I'm now left with a directed graph that has 0 cycles. There are no cycles in this digraph. So the circuit rank of this directed graph is equal to 2. It took 2 arrows to break all of the cycles. So that means that the circuit rank is equal to 2. The next thing I'd like to touch on is the notion of weights in a digraph. So if we go back to our example where we're modeling transactions between financial institutions, one thing that was missing from our model was the size of the transactions. If we're going to model money transactions, we need to know the amounts of money that are moving from institution to institution. So that was missing from the data before. Let's include that now. So here, the first transaction was from Wells Fargo to Chase. And what I'm introducing here is notation where I'm bracketing off a number. That number is called the weight of this arrow. So here, the size of the transaction that occurred between Wells Fargo and Chase was $13. In the second transaction here, Chase was sending Wells Fargo $9. In the third transaction, Wells Fargo sent Citibank $137. In the fourth transaction, Chase is sending Citibank $3. And in the fifth transaction, Chase is sending Citibank $95. So now we have a layer of sophistication in our model, and this is the idea behind a weighted digraph. We're associating numbers to each one of the arrows, and in this particular example, those numbers represented the size of the transaction. So we call these digraphs, if we're assigning special numbers to the arrows, these are called weighted digraphs. And one thing that's useful to point out is weights don't have to necessarily correspond to something like in real life, like money does. They can also encode interesting things about the digraph. For example, you can use weights to communicate the data of a cycle in the digraph. So here's an example. So this is the example we used when we first introduced the notion of a cycle a few slides ago. And remember, in that example, we started at V1. We traveled with the arrow A1, then we traveled against the arrow A4, then we traveled with the arrow A3, then we traveled against the arrow A2. In that cycle, we also ignored all of the other arrows, A5, A6, A7. So the idea here is that I've equipped this digraph with weights on all of the arrows, and the weights I've chosen communicate the path that we took in our cycle. Because we traveled with the arrow A1, I've equipped A1 with the weight +1. We then traveled against A4, so I've equipped A4 with the weight -1. We traveled with A3, so I've equipped A3 with the weight +1. And then I traveled against A2, so I've equipped A2 with the weight -1. And because I ignored the arrows A5, A6, and A7 when I took that path, I'm equipping each of those arrows with the weight 0. So following that path, again, V1 to V3 with A1, so we pick up a 1 here. V3 against A4, so we pick up a -1 here. V4 to V2 with A3, so we pick up a 1 here. And then V2 back to V1 against A2, so we pick up a -1 here. So the weights inside of this particular digraph are communicating something about something geometric about the directed graph, namely the path I took when I cycled from V1 back to itself. And one thing to learn from this example is that negative weights are perfectly acceptable. There's nothing wrong with me saying that the weight on the arrow A4 is -1 here. It's useful for me to do it, so we allow that to happen. So this gives us another concept, and this is the concept of net flow. So one thing that sometimes turns out to be useful if you're working with a weighted digraph is to go to each node and ask, what is the net flow through the node? And when we say net flow, what we mean is let's add all of the weights pointing at the node, and then let's subtract all of the weights pointing away from the node. The notation I'll use here is this Greek letter. This is a Greek phi, P-H-I. So phi of a node V represents the net flow, and this is equal to all of the weights that are pointing in to the node, and then we subtract all of the weights pointing out of the node. So let's go back to our financial example. In our financial network, the idea here is that money is flowing through institutions. And one thing that a bookkeeper might care about, or a banker might care about, is what is the amount of money that flows through a particular institution? This is exactly what net flow is designed to do. So here I have the calculations here for net flow through each of these nodes. Let's start with Wells Fargo here. So here we're looking at Wells Fargo. Wells Fargo comes into contact with 3 of the arrows in this directed graph, T1, T2, and T3. So to calculate the net flow, what we do is we add all of the weights that are pointing at Wells Fargo. So here, of the 3 arrows that Wells Fargo comes into contact with, only T2 is pointing at Wells Fargo. So we're going to start with 9, and then none of the other arrows point at Wells Fargo, so there's nothing left to add. Now we're going to subtract all of the weights pointing away from Wells Fargo. So here, T1 is 13, and T3 is 137. Those are the 2 arrows that point away from Wells Fargo. So we're going to subtract 13 plus 137 as a quantity. And when we calculate 9 minus the quantity 13 plus 137, we end up with -141. So in this model, the idea is that the net flow through Wells Fargo is -141. So Wells Fargo is down money for the day if this represented all of the transactions that they conducted throughout the day. Let's look at the net flow through Chase Bank. So what is the net flow through Chase Bank? Well, Chase comes into contact with 4 of the arrows in this digraph. Here, only 1 arrow points at Chase, and that's T1, which is $13. So we start with $13. All of the other arrows point away from Chase Bank, so we have to subtract all of those. So we'll subtract 9, we'll subtract 3, and we'll subtract 95. And when we do the arithmetic, we end up with -$94. So on net for the day, Chase is losing $94 through these transactions. We had a tiny bit come in, but we had more flowing out. And finally, we have Citibank. Citibank here comes into contact with 3 arrows, and lucky for Citibank, they're all pointing at Citibank. So here, there's nothing to subtract. We're simply adding 137 plus 3 plus 95. And when we put all that together, we get 235. So of these three institutions represented in this directed graph, only Citibank is making money in these transactions. Namely, they're making $235. I'd like to point out that even though the previous example is directly applicable to something tangible in the world, there's nothing preventing us from applying our formula in a more abstract setting. So here I've constructed a very simple digraph, and I've just randomly chosen some weights for these arrows, and I just want to show you what the calculations here look like. So if I look at the first node in this directed graph, this node comes into contact with the arrows A1, A2, and A3. Of those three arrows, only A2 is pointing at V1. So we're going to add this weight. It just so happens that weight is negative. So here we start with -7. Then we'll subtract off all of the weights pointing away from V1. So we'll subtract the quantity 3 plus 6 here, and we end up with -16. If we look at V2, V2 comes into contact with three arrows. A1 and A4 point at V2. So we're going to add those weights together. So we're adding 6 and -9 together. And again, there's nothing wrong with this weight being negative. Then we'll subtract off the only weight that's pointing away from V2. So we'll subtract -7. And when we do our arithmetic here, we'll get 4. Finally, for the third node, this one only comes into contact with two arrows. One points into the node, one points away. The arrow that points into the node is A3, which is equipped with the weight 3. That's purely coincidence. So we start with 3. Then we need to subtract off the weight of the only arrow that points away from the node. So we subtract off -9. And then when we do the arithmetic, we end up with 12. So the net flow through the three nodes here are -16, 4, and 12.